This is the second part of the lecture 7. We will conclude in this lecture the property of uniform convexity. Let us begin with the let's say technical lemma. Let's put it like this, lemma. We have the following inequality. This inequality is referred often as the Clarkson first inequality. And it states the following: let P will be a number larger or equal than 2, smaller than infinity, of course. And then we have the following: for every real numbers A and B belonging to R, we have here absolute value A plus B over 2 to the power P plus A minus B over 2 to the power P, smaller equal than 1/2, and here we have here A to the power P plus B to the power P. And we begin with the proof, and in order to prove the inequality, call this inequality star. First, we prove a little different inequality. First, we show that for every alpha and beta larger or equal than 0, we have, and let me write it down, this inequality is alpha to the power P plus beta to the power P is smaller equal than, and here we have here alpha squared plus beta squared to the power P over 2. So this is the inequality, called this inequality 1. And notice that this inequality is homogeneous with respect to alpha and beta. That means simply we can divide this inequality by alpha. Suppose here alpha different than 0. We can write it down that this is alpha P plus beta P smaller equal alpha square plus beta square P over 2. So let's say like this: we divide this inequality by alpha to the power P, alpha to the power P, so this will be smaller, and then we have alpha square plus beta square P over 2 divided by alpha to the power P. And what do we get? We are getting this is 1 plus beta over alpha to the power P, and that means this must be small. And then you notice you can actually enter this also inside the second bracket, and then it will be 1 plus alpha divided by beta divided by alpha squared to the power P over 2. Put x is equal beta by alpha, and we are getting here that the inequality. So the inequality 1 is actually equivalent to this inequality. So this is 1 plus x to the power P smaller equal than 1 plus x squared, and this will be P over 2. P over 2. So we just need to prove the inequality, call this inequality 2, and we just need to prove this inequality. For the purpose of doing it, let's just simply say take function phi, simple function of one variable, and write it down. This is 1 plus x squared P over 2 minus x to the power P minus 1, which is exactly, we put everything on the right hand side, and we just need to show that this function is positive. So sorry, put, so we need to show that phi of x is positive, and that is exactly the inequality 2. So indeed we have that phi of 0. So what do I get here? So put here a bullet. Phi of 0 is equal to, oh, that's equal 1 minus 1. Oh, that's 0. And then let's compute the derivative. Remember, x is positive, so derivative of x, remember this is 0, is equal, so we have here like this. P1 plus x squared p minus 2 over 2x minus p x p minus 1. Very nice. And then, of course, you can now, evidently, since x is positive, we can write it down as larger equal, then this will be p, and I put here like this. Drop this 1, so I'm just simply dropping this 1. So we are getting here, this will be x squared to the power p minus 2 over 2 x minus px p minus 1, and that gives me px to the power p minus 1 minus px p minus 1 is equal to 0. So the function, so phi of x is a non-decreasing function. So clearly the inequality must be satisfied. So that means it is larger or equal to 0, and the inequality true. Thus the inequality 2 is true, which means also that the inequality 1 is true. So now, once we have it, substitute. Alpha is equal a plus b absolute value by 2. Beta is equal a minus b by 2. And then we have here a plus b divided by 2 and to the power p plus a minus b by 2 to the power p. And now we have the inequality 1, and maybe I should write it in red so you can see clearly this is by 1. Then you have here bracket, and then you have here a minus b 2 square plus put here plus a minus b 2 square, and this is p over 2, and we can compute it. So what do I get here? This is actually equal. Put it like that. This is equal. A square plus 2ab plus b square divided by 4 plus a square minus 2ab plus b square, and this is p over 2. Now we have a little cancellation here. This and this cancel, and then you come here and you see, I'm getting here, this one is equal. A, let's put it like this, a is absolute value square over 2 plus b square over 2. That's not nice, it looks like 3 over 2. And this one is p over 2. And then I look at that expression. Look, I see kind of an expression that reminds me something. Notice that this function, call it like this, psi of t, which I denoted t to the power p over 2, so that means t must be larger than 0, is convex. It's convex. How do I do it? How do I check it? Just simply take the first derivative and the second derivative. Second derivative is nothing else than, so let me do the p over 2 times p minus 2 over 2, and this is t to the power p minus 4 over 2. So t for positive, t, what do I get here? Maybe it's too messy, so too messy. So let me write it again nicely. P, what's happened? Okay. So this is p over 2, and then you have here p minus 2 over 2, t, p minus 2 over 4, for t positive, so that value is positive. So that means this function is convex, and in particular it satisfies the property that if I take here a, let's say like this, square, divide, and let's say like this is my a squared, so put it like this, alpha, and this will be a square over 2 plus beta, b square over 2, such that alpha plus beta is equal to 1, and alpha, beta are larger than 0. So by convexity it will be smaller than, so this is 5, so this will be smaller than phi of a square over, a square plus phi, beta, no, it's called beta, and this will be phi b squared. So in our case, alpha is equal to 1/2. So this is alpha will be equal to 1/2. Beta is equal to 1/2. So this simply means this simply means that you can simply write it down. Smaller equal by convexity. So put it like this: convexity. And this is 1/2 goes out, and here we have here alpha, a absolute value to the power 2, so that one gives me nothing else than a to this p plus b to the p, and that's exactly the inequality star. So we got it. So that's very, let's say that in such a case, let's say we can formulate our main results. We'll call it theorem. So this is the main results for this part. So this will be theorem. Let x, and put it like this. This is like m mu be a measure space, an arbitrary measure space, and consider the space L, P, and this will be X, and we denote it like this with mu, so that comes from this measure space, where with P, which is larger than 2 but still smaller than infinity. Then we have the statement, this L, P, X, mu is uniformly convex. And that's for any measure space. So proof. So the proof is very, let's say, just simple applications of the previous inequality by Clarkson. First inequality. For every f and for every g belonging to L, P, x mu, we have, and we can write simply, what do we have? So we have for every x belonging to x, I can write it down, f of x divided plus g of x divided by 2 to the power p plus f of x minus g of x divided by 2, p, so this is my a, g of x is my b, so that one is smaller equal, and then we have here 1/2, and then we have here f of x to the power p plus g of x to the power p. And let's denote this inequality, call it number 3. So we have this inequality. So by integrating the inequality 3 over x, we obtain, and what do we obtain? We obtain the following, that this becomes the norm of f, oh yeah, that will become the norm of f plus g2, but this will be the norm, p norm, but since over there, since we have here this power p, but we don't have we do not have the root, so that means simply this will be to the power p. Plus, again, the same here, f minus g2, and this will be p. p smaller equal than 1/2, and then we have here the norm of f p to the power p plus, and this is the norm of g p to the power p. So now let's show the uniform convexity. So in such a case, let's start the following. So suppose we have here, suppose have an epsilon is larger than 0. Suppose here larger than 0. Then we have that we need to find the delta for it, but we just simply, maybe let's say like this, and consider two functions f and g belonging to LPX, not nice, xg belonging to LPX mu, such that, and then you see here we have here f minus g p, of course, is larger equal than epsilon. This is larger equal than epsilon. Okay, so we have such a value. So now, what do I need to do? I just need, okay, do I need to, let's say, yeah, so then by inequality 3, by 3, we have, what do I have? I have this inequality. So look, I'm looking at this inequality. So this is not inequality 3, inequality 4. So by inequality 4, we have, so this is my inequality. No, that one is 4. This one is 4. Yes. Yes, so again, so maybe we should put it in red. So this is inequality. This is my inequality 4, which is like a Clarkson inequality. And now we have the following. So we are interested in this particular value. So let's write it down. F plus G over 2 P. P is smaller equal to, this will be 1/2. And this is F P plus G P, and now minus, and here we have here F minus G2 to the power P. And what do I see? I see that, yeah, so let's see. That means we have here this one, and what do I see? I have two things. We should remember that, such that this one is larger, and we also need to assume that these two things and G, P smaller equal than 1. So, sorry. So that's it, remember. So that's what we should remember. One moment. So and also this one. So that's for the convex uniform convexity. These two, we have these two conditions satisfied, and then we have 4, so you can write it down. So first of all, by the put here like this by that one, so call it like a star, call this one like a double star. So what do I get? I'm getting simply that by star, I'm getting this one is 1/2, and then you have write 1 plus 1, and this is minus, and that one is that epsilon over 2 to the power P, which gives me 1 minus epsilon of 2 to the power P. So it is sufficient. So it is sufficient to take delta, which will be like, let's write it down, 1 minus epsilon over 2 to the power, that's not nice, like ugly, 1 minus, put here epsilon over 2 to the power P, close it, 1 over P. Look, that's number. Epsilon, we assume it's sufficiently small, so we can always assume it's smaller than at least 2, right? So smaller than 1, so okay, 2. This is, we can always choose sufficiently small. So in such a case, that number will be smaller than 1, that number will be also smaller than 1, this number will be smaller than, so I'm getting delta, which is positive. And that proves the uniform convexity of the space LP. So let's close it, and let me make actually remark. All the spaces LP x mu for 1 smaller than infinity, for p between 1 and infinity, are in fact uniformly continuous. Uniformly continuous. But the proof in the case of the proof for 1 smaller than b smaller than 2 is more complicated. And we need it to conclude reflexibility of LP x mu. So we will do it by a different way. Easy way. And however, you should understand that there is another version of the inequality that can be used to prove the uniform convexity, even in this case, when 1 is smaller than p smaller than infinity. We do not do it. You should be aware of it, that this is actually true. You can always check it in the literature, and if you need such a fact, you can always refer to the proper sources. However, we will not use it in this course. So, thank you.